Hello, and welcome to another exciting chapter in Math 305. This is more in the intro where we're learning to just solve linear programming problems graphically. Now, this is not going to be very useful when we get into higher dimensions, but hopefully we will be able to gain a lot of intuition from solving many different situations graphically. Today, we're just doing one single simple problem that has a solution. In other lessons in class, we will be going over ones that have other things happen to them. It would be more interesting than this one. But let's pick up with Geppetto's wood carving problem. We modeled it last class. We let our variables be the number of toy soldiers and the number of trains that Geppetto makes in his toy making shop. And we wanted to maximize the profit, and this was the function we wrote for profits. It's our objective function. And then our constraints, there was a constraint for carpentry time, a constraint for finishing time, like painting. There was a constraint for the demand on the toy soldiers. And then there's non-negativity. I can't make negative soldiers. I can't make negative trains. Okay, so all the constraints make our feasibility region. And if we put those on a graph, this is what we're looking at right here. These are the equations if we graph them, including the non-negativity, because when we put those together, what we get is this region in here. Okay? And so every point in or on the edge of this shape is a feasible point. It's a possibility of us to make. So the point 2020, I could make 20 soldiers and 20 trains, and that's feasible. We'd have enough time and enough demand to make that. I couldn't make anything outside of the feasibility range. So if I wanted to make 60 soldiers and 40 trains, I don't have enough carpentry or finishing time. So these are all of our possible answer choices. So the optimal is going to be whichever of these points in here gives us the highest profit. So somehow then, we're going to want to incorporate our profit function into this graph. What's weird about the profit function, if we go back and look though, is that I have three variables essentially. I have an x and a y, or x1 and an x2, and then I also have a variable for the profit, which we don't really know what to do. How can I graph something three-dimensional on a two-dimensional graph? Well, it's not really three-dimensional. That's just going to be some number, z is, but we need a special way to rewrite it to make it easier to understand. So we're going to write it in slope-intercept form, just ignoring the z for a second. So pretend that's x and y. If we rewrite this in slope-intercept form, subtracting this term over, then dividing everything by 2, this is what we get right here. Okay? Notice z is part of the y-intercept. Well, when we rewrite things like this is called an iso-profit line. That's what we call it for maximizations. In the text, you'll see iso-cost for minimizations, but often, lazily, we will just call them all iso-profits. What we're doing is isolating the effect of certain pieces here with this rewrite. So if I go and I graph this line, and I let z, if we use some graphing software like Desmos online graphing calculator, and I let z take on any values, I can slide the value of z. That'll just slide the graph, and look what's not going to change when I slide that. The slope is going to stay exactly the same. So we will just be sliding the line up and down the y-axis by adjusting the profit we make. Now how is this going to work? Let us actually add it to our graph and see. So let me pull up my graphing calculator here. I hope everybody can see this. So this is the same feasibility region right in here. And the red line is my profit line. You can look over here. It's the same equation, negative 3/2 x plus z over 2. And so I added a slider for z, and as I move z, it moves up and down, but z is the profit actually. Anywhere on this line, if I pick any xy pair on this line, I will get whatever z is for my profit. So if you come here and I slide it to the point 2020, that's inside my feasibility region, and it's on this line, it would give me a profit of 100. And so I can slide this line up and down. Now I'm wanting to maximize profits, so I would like to slide it up as far as I can. Now I could slide it up forever, right? I could slide it up to infinity. I just set the top at 200. But notice none of the red line is inside our feasibility region, so I can't do any of these these xy pairs. So what we're wanting to do when we're optimizing by graphing is slide our profits as high as we can while still having some sort of our red line, our ISO profit line, touching a feasible point. We like to push it as far as we can, but still have a feasible point where the red line is sharing that point, is intersecting that point. Now thinking about this, what does this mean about optimals? That means they're going to be on the edges of our shape, because we're going to push as far as we can in whatever the improving direction is. So if I push this as far as I can push it, where it's still intersecting some part of the feasibility region, it looks like I'm going to be able to push it to right there, and it will share that single point with these two constraints right there at the point 2060. It looks like it'll give us a profit of 180. And if I push it any further, I will not be in the feasibility region. So notice we can slide these profit lines as far as we can, and we will end up tipping just the edge of the graph and sharing a profit line point and a feasible point, and that will be our optimal choice. So the point 2060 with a profit of 180 is the best we can do. I think I have that written here. Yep. So we'll write it in this way. We can write it as an ordered pair. When we get to higher dimensions, we'll just write them as ordered triples or some sort of ordered tuple. And the profit was 180. I don't know what units this was in. It's supposed to be the Geppetto, the wood carver that carved Pinocchio. So I'm guessing whatever Italian currency was back when that movie was made. So just in summary, to optimize our profits, we can make 20 soldiers, 60 trains, and that's the best we could do. All right. Now a few other things before I get to some facts here. It seems like, let's just logically think about this then. Like I said earlier, if we're pushing our profit line as far as we can get it, the answer is always going to probably be on the outside edge of our shape. And maybe not just the outside edge, but that was at an intersection point or a corner point. And these are actually really important. I'll go ahead and tell you now that if our problem has a solution, it will exist at a corner point. Okay? So we can prove this in class. I think only my math majors will probably be interested in seeing it proven. But or we could. It's easy. It's a very famous proof for this course, so it's one that's probably in the textbook or easily looked up online. But for time's sake, I'm not going to prove it now. But our solutions, if they exist, a solution will exist at a corner point. We call these extreme points. These corner points. Okay. Other things I want to point out is often we classify. This will be important later in the course. When we're at an optimal, or actually at any feasible point, we classify things as either constraints, as either binding or slack, okay? Or binding or non-binding, all right? And it's really simple to see this. Which two constraints are we actually touching at this point? We're touching the finishing time constraint and the carpentry constraint. These come from those two equations. At this point, I am not touching the constraint that was constrained by the demand on the soldiers, and I'm not touching the non-negativity constraints. So these constraints are slack. These two constraints are tight or binding at this point, at this solution. Okay, so just a little bit of vocabulary. I will go ahead and say something else that's very nice about this. Let me back the profit line out of the way. So if you're looking at our feasible shape here, our feasibility region, notice that it is convex. Okay, this is, if you were to take a graduate course in this, you would spend a lot of time discussing convexity, because it's very important to have convex shapes to be able to find optimals this way. Okay, it's, how do I want to word this? If you were to take a nonlinear optimization course, you would spend a whole probably 2 weeks doing convexity proofs on sets of feasible sets, trying to figure out, because if you lose convexity, you have a hard time finding optimals. Okay, so a few facts about linear programs. Since we're in the very intro of this course, a few things you need to know. If we have a linear programming problem, then the feasible region will be convex. We're guaranteed that by the way that linear programming problems are structured. Okay? So that's nice. This is part of what makes linear programming easy. Next, if you have a linear programming problem, then the feasibility region will have only a finite set of extreme points. Okay? So finite set of extreme points with something I mentioned earlier, or with what I have here, that's nice. So our linear programming, if it has an optimal solution, it will exist at an extreme point. Okay? One of those optimals will be at an extreme point. So that's not a horrible thing when you group these three together. Really, the only reason for the convex thing is without convexity, we don't have these next two. Okay? So we're guaranteed all three of these, mainly because of everything being linear. And the way we add on these linear inequalities, they guarantee us a convex shape. And because we're only adding extreme points when we add linear constraints, we're adding a finite set of them. So this is, you could think of a lazy algorithm that's not really efficient, but we could just check every extreme point for an optimal, right? And algebraically, there's an easy way to do that. We know how to solve systems, right? But that would be tedious, but maybe we'll go there next until we build the simplex algorithm. One last thing I do want to point out, maybe I won't go there right now. But anyways, so that's how you solve graphically, is we graph our constraints, and then we put our ISO profit line and slide it as far as we can in the improving direction. Or we could just check every single intersection's profits. That's another way of doing this, but if you have like 10 of them, that may be time consuming. Alright, well, that's all I have for you today. Next class, when we meet in person, we'll be going into looking at different things that can happen to us when we start to model some different problems. We'll be doing a lot of modeling and putting the graphs down to explore. Alright? Anyways, have an awesome day.